Okay, this video is going to discuss how to determine absolute date and by using radioactive elements. The first thing you have to remember is what's the difference between an absolute and relative date, or absolute and relative age. Relative age, as we said before, is the comparison of two things. Let's say this is a little baby, or determining the age by comparing two things together, and this is an adult. So relative age would say, well, this person's older and this person is younger. No dates involved, it's just comparing two things together to figure out how old they are compared to each other. Absolute age is actually getting the number of years old an object or fossil is. Okay, so absolute age is determined by using radioactive dating. Radioactive dating helps determine absolute age determining absolute age by measuring how much radioactive elements, I'm just going to abbreviate that, have decayed in the sample. Oops. Okay, so they measure how much radioactive elements have decayed, and from that they actually can calculate the age of the rock or the fossil, the object. The idea of what does radioactive actually mean? Radioactive is referring to an atom that has an unstable nucleus because it has essentially too many neutrons in it, too many neutrons to stay stable. E-U-T-R-O-N-S. And so this brings back the idea of an isotope. We learned back in the chemistry unit that isotopes are elements of the same type that have different numbers of neutrons in them. A common isotope that we talked about then, and also is used in radioactive dating, is carbon. Carbon, by definition, has 6 protons. That's what makes it be carbon. The most common form of carbon, carbon-12, has 6 neutrons also. But there is an isotope of carbon called carbon-13 that has 7 neutrons, and then there's the radioactive form of carbon, the one that has too many neutrons to be stable, it has 8 neutrons in it. And so what happens is this element here, the neutrons actually will decay. They release energy in particles to turn them into a more stable element. They actually call that the decay element. In the case of carbon-14, when the nucleus actually gives off its energy and it has a neutron that changes into a proton, ultimately changing carbon into nitrogen, because the number of protons actually goes from 6 protons to 7 protons, as one of these neutrons here turns into a proton. And if you have 7 protons, you're nitrogen. So the decay element, again, is what a radioactive element turns into when it gives off its energy and decays. An important understanding in how we calculate radioactive dating is what they call half-life. Half-life is the amount of time it takes for half of a radioactive sample to decay. So in the case of carbon-14, on average, it takes about 5,730 years for half of whatever you start with of carbon-14 to decay. And they take the average because any particular atom, if you just had one carbon-14 atom, it could decay this second, or it could decay in 10 million years from now. So it's unpredictable when this unstable atom will decay. So they take the average number, and so what you get is, on average, you get about that much decaying half of it will decay in that many years. That's called half-life. So in order to understand absolute age, you also have to be able to see how you calculate that. So I have a couple practice problems here for us. First one says, what is the age of a fossil that has only 3.12% of its original C14 remaining? Remembering that the half-life for carbon-14 is 5,730 years. The way that you do that is you look at, I like to put it in a chart, you don't have to, but when let's say this is a bone or something, when it initially dies, it has 100% of whatever C14 it's ever going to have. It hasn't gone through any half-lives. and its absolute age at this point would be, it's just died today, it's 0. But after one half-life, it had 50% of what it originally started with, and that would take on average 5,730 years. And so we're trying to see, well, how old is it when it gets to 3.125? So I go 2 half-lives. That's going to have 25%, and that's going to equal 11,460 years would have gone by. I just added another half-life. After 3 half-lives, I'd have 12.5%, and that's going to be 17,190 years. Every time I'm just adding 5,730 years. After 4 half-lives, that's 6.25, so that's going to be 22,920. After 5 half-lives, I cut that in half. I get to the magic number that the problem's asking me about. And if I add another 5,730 years, I get 28,650. So that fossil with 3.125% left in it would be about 28,650 years old. Another example problem, what percent of radioactive uranium-238 is left in a rock? So I'm looking for the percent here, is left in a rock in a sample that is 13.5 billion years old. I accidentally wrote down here, but the half-life for uranium-238 is 4.5 billion years. So after one half-life, I'd have 50% remaining, and it'd be 4.5 billion years old. After 2 half-lives, I'd have 25% remaining. That'd be 9 billion years old. After 3 half-lives, I'd have 12.5% remaining, and that gets us to the number in the problem, 13.5 billion years. So that would be the answer. I'm sorry, technically this is the answer. This is the percent they're looking for. So 12.5% would be left after 13.5 billion years. Finally, one of the things that keeps coming up in class is why can't you use C14 to date things that are more than about 50,000 years old? And that's because you essentially will run out of C14 if you kind of take the pattern through. So starting with C14, after 1 half-life, you're going to have 50%. It's going to be this many years old. After 2 half-lives, you'll have 25%. You can see the pattern here as I just go through it. 4 half-lives, you get 6.25. 5 half-lives, 3.125. 6 half-lives is 1.56. 7 half-lives is 0.78. 8 half-lives is 0.39. I should have lined these up better. But you get the overall idea that by the time you get to about, that's a 3, 50,000 years old, there's so little, if you go one more even, there's so little carbon-14 remaining in the sample, there's not enough to get a collective good date for. And that's why they don't generally use C14 after about 50,000 years old. They end up using another isotope, maybe dating the volcanic layers using uranium-238 above and below where a fossil was discovered. Finally, a couple other details that you have to know. Some examples, some information about carbon-14. Know that it's used to date material that comes from living things. Its half-life is 5,730 years. Its decay element is nitrogen. And anything that comes from a living thing would be things that could be dated. So a tree branch, a fossil bone, as long as they're not too old. Uranium, it's used to determine the date of rocks, volcanic activity. Half-life, 4.5 billion years. And its decay element is lead. Oops, L-E-A-D, and that's abbreviated PB. That's it.